So, we were actually looking at the recursion relationship. We wanted to terminate the series at some finite power of c, and we managed to do that by putting lambda is equal to 2n plus 1. This ensures that we have an acceptable solution, and that actually means that 2e by h nu must be equal to 2n plus 1, which implies that e must be equal to n plus half h nu. So, therefore, you are able to get acceptable solutions only for these values of energy, and there are no acceptable solutions for any other value of energy. And so, we say that the energy of the harmonic oscillator is quantized, it has to be equal to n plus half h nu, otherwise no acceptable solutions. Okay. And further, if lambda is equal to 2n plus 1, you can actually substitute it here. And you can replace this lambda minus 1 with the 2n, sorry, you can replace lambda in here with the 2n plus 1, and you will get a differential equation which will read like so. Therefore, we know that h, the function h is a polynomial, it will satisfy this differential equation, and if you wanted to determine h, actually what you can do is you can use the recursion relationship. You will take a value for a0 and then go use the recursion relationship to determine the polynomial. But it so happens that the functions which obey this differential equation were very well known to mathematicians, right. Even before quantum mechanics came up, mathematicians had studied those differential equations and the associated polynomials, and they were studied by the person called Hermite. And so, these polynomials are known as Hermite's polynomials. Okay, so, I will spend a little bit time, maybe 15-20 minutes, describing the properties of this polynomial. I will not go into that much detail when we encounter other polynomials later on in the course, but this one I will describe in all its details, just to give you an idea as to how one works with this kind of polynomials. So, what I will do is I will start with what is referred to as a generating function. See, here I have a function which depends upon two variables, one variable is s and the other is c. It is a function of two variables, and therefore, I am going to write this as some capital S which depends upon small s and c. Okay. Capital S is the function, small s and c are two variables, and this capital S obviously depends upon these two variables. Now, you know that if I had e to the power of minus x, I can expand it as a series. Similarly, this also, if you want, you can expand it and you will get a series, right. Suppose I do that and I write this as a series in S. So, what is going to happen is I will have a series which will involve any power of s. Imagine you expand this as a series, then what is going to happen is that you will have s power 0, s power 1, s power 2, s power 3, etc. So, imagine I can write this as a series involving s to the power of n divided by n factorial summed from n going from 0 to infinity, correct. It should be possible to do that. Okay. But then if I write it like this, there will be some coefficients here, but those coefficients you will realize have to be functions of the other variable, right. If you want, I can illustrate the point that I am saying. See, if you had expanded this, the series would be 1. I mean, I know that e to the power of x is equal to 1 plus x square by 2 factorial plus etc., and all that is happening is that here x is actually minus s square plus sc, that is all. So, the first term will be that, plus the second term will be minus s square plus s into, okay, my first mistake, there is a 2 here. So, let me just, I mean, that is the definition. So, there is a 2 here, there is a 2 there. So, this is what the series is, correct, and what I can do is I can do this, I can write the full series, expand and then collect together all the terms which have the same power of s. For example, s to the power of 3, I can collect them together. If I collected them together, then there will be a coefficient, and that coefficient will depend upon the other variable c, that is all. So, therefore, this can be written, this function can be written as a power series in S, and there are going to be coefficients, and those coefficients actually I am going to denote them as Hn of c. Right. And interestingly, what happens is that these coefficients are just your Hermite polynomials. That is the reason why we think of this generating function, right. These coefficients, they are introduced this way, they are just functions which obey this differential equation with a 2n here, okay. So, therefore, these functions are just the ones which occur there as the coefficients. Well, it is not enough to make this claim, I should prove that. As I said, I will in the next 15 or 20 minutes I will actually show that that is the way it is. Now, suppose I take this function, this is a generating function and this is extremely useful. In fact, later on we will encounter Lagore polynomials and Legendre polynomials. They all have their own generating functions, they all have similar things, okay. That is the reason why I thought this is a nice thing to introduce. So, suppose I take this function and differentiate with respect to c. What will be the answer? Well, here if you differentiate, the answer is going to be minus, sorry, there is no negative sign, it is going to be 2 times s times this object, and that is nothing but your s, correct. This is definitely valid. But then I know that s is given by this expression. So, therefore, I can say that okay, the left hand side I can evaluate using that expression, right. So, if you evaluated the left hand side using that expression, what is the answer that you are going to get? You are going to have some n going from 0 to infinity s to the power of n divided by n factorial, correct. You are differentiating with respect to say, you are not doing anything with respect to s, and so maybe what I should do is I should change this to partial differentiation notation, that is better, so that there is no chance of any confusion. I am differentiating partially with respect to C and not changing S. So then what is going to happen is, you see, when I calculate the derivative using this expression, s to the power of n by n factorial will remain unchanged, but the derivative operator is going to operate upon Hn. So therefore what you are going to get is dHnc by dC. So that is your left hand side, and that must be equal to 2 times S, correct, and therefore what is that? That is actually sigma n going from 0 to infinity, right, s to the power of n divided by n factorial Hnc. Right, and this S, if you like, you can take it inside, right, because S is there. So why should it be sitting outside? I can put it into the summation, inside the summation, and say Sn plus 1. So you see here, left hand side you have a power series, right hand side you have a power series in S. So if you think of one power series, if you say one power series is equal to another power series, then what should happen? All the coefficients, if you think of coefficient of s to the power of 4, whatever is there on the right hand side, it has to be equal to whatever is there on the left hand side. So therefore, let us say I want to look at the coefficient of s to the power of 4 on the left hand side. What is it? It is actually 1 by 4 factorial dH4 by dC to the power dC, right. That is the coefficient of s to the power of 4 on the left hand side. What will be the term on the right hand side? Coefficient of s to the power of 4. You will get 2, you will get this n plus 1 should be equal to 4, that means n should be equal to 3, and therefore you are going to get 1 by 3 factorial H3C, correct. This is what you are going to get. That means dH4 by dC is actually equal to something in terms of H3, right. So instead of equating the power of s to the power of 4, suppose I had equated the power of s to the power of n. Here I have just illustrated the point by equating the powers of h to the power of h to the power of 4, equating the coefficients of s to the power of 4, but instead of that, suppose I had equated the coefficients of s to the power of n, what would be the result? The result would be very simple. I would have the result that 1 by n factorial dHn by dC is equal to 2 divided by n minus 1 factorial Hn minus 1C, right. So therefore what this says is the first derivative of Hn right, these functions Hn are such that the first derivative of Hn is actually equal to 2n times Hn minus 1C, correct. So I have proved this relationship. How did I prove it? I used the generating function, that is why the generative function is useful. If you took the first derivative of this Hn, the answer is Hn minus 1 into 20. Is there a mistake? Now this I have done by differentiating with respect to C, but now let me differentiate with respect to S partially and see what the answer is. So, dou S by dou S is equal to, if you differentiate partially, what will happen? You are going to get minus 2S plus 2C, right. The derivative of this exponent is minus 2S plus 2C, because I am differentiating partially with respect to S with small s into capital S, right. Procedure is just the same as before. I will now evaluate the left hand side using this expression. I will substitute the same expression into here and then equate the coefficients of S to the power of n, correct. This is what I will do. Let me see what the result is. So, because we understand the procedure, we can proceed quickly. Sigma n equal to 0 to infinity, I have to differentiate this with respect to S. So, the answer is going to be S to the power of n minus 1. One n will come down, but then you have n factorial, right. So, what will happen? This n and that n minus 1 factor, sorry, n minus, I am anticipating the result, that is why I say n minus 1 factorial. This n and n factorial will be combined and I will get n minus 1 factorial, okay, and the coefficient will be h and c, and that is equal to minus 2s plus 2c sum n going from 0 to infinity s to the power of n h and c divided by n factorial. The right hand side, let me just rewrite by splitting the terms. You will have this term minus 2 sigma n going from 0 to infinity. If you took this as inside, you are going to get s to the power of n plus 1 h and c divided by n factorial plus sigma, well, there is a c sitting outside, maybe I will take it inside. This 2c I will take inside, so I will have s to the power of n by n factorial 2c h n c. Right. Tell me if I have made mistakes. So, just as before, I mean, maybe we will just look at the coefficient of s to the power of 4 on the left hand side as well as on the right hand side, equate the two, see what happens and then generalize it. So, what will be the coefficient of s to the power of 4 here? It is going to be 1 by 4 factorial, right. You have to say n minus 1 in here is equal to 4, because I want to get the coefficient of s to the power of 4. So, n minus 1 is 4, that means I will get 1 by 4 factorial h 5 c is equal to the right hand side. In the right hand side, you see you have to have s to the power of 4, that means you will have to put n plus 1 should be equal to 4, that means it is 3, right. S is 3, right. So, you will get h 3c divided by 3 factorial, right, because n plus 1 has to be 4 to get 4 s to the power of 4, and as far as this term is concerned, to get s to the power of 4, it is quite straightforward, you have to just put n equal to 4. So, oh, there is a minus 2 here, thank you for reminding me, plus 2c h 4c divided by 4 factorial. Is that okay? I hope there are no mistakes. In fact, I am tempted to check it from the book. So, let us now generalize. In general, what will happen? I will have 1 by n factorial. I am going to equate the powers of s to the power of n. This is for s to the power of 4. So, what is going to happen is I would have h n plus 1 c equal to minus 2 h n minus 1 c divided by n minus 1 factorial plus 2 c h n c divided by n factorial. Right. This is what will happen if you equated the coefficients of s to the power of n, and this relationship you can, what will you do? You will multiply throughout by n factorial and we look at the result. So, if you multiply it throughout, the answer is going to be h n plus 1 c is equal to how much? Right. Now, my ultimate aim is to show that h n actually obeys this equation. That is what I want to show. H n obeys this equation is what I want to show. So, how will I do that? I have these two equations and I can use these two equations, I can manipulate them and then get that differential equation. So, how will I manipulate them? Obviously, you see I need the second derivative of h n, because you look at the differential equation, it has second derivative of h. So, that means I will differentiate this once more. Will be equal to what? It is going to be equal to 2n, right, n is just a number, dh n minus 1 by dc, right. If you just differentiate, this is going to be the answer. I give you the reason for doing this. I want to get the second derivative of h n. Why? Because the second derivative is there in this differential equation. But then if you are interested in the second derivative of a Hermite polynomial, right, if you are interested in the second derivative of a Hermite polynomial, it is now related to the first derivative of the Hermite polynomial, but the first derivative itself can be written in terms of a Hermite polynomial. So, in this equation all that I need to do is put instead of n you put n minus 1. So, if you put n minus 1, what will happen? You are going to get 2n, this derivative I am going to use that equation and get 2 into n minus 1 into h n minus 2c, that is all. Okay. Now, what I will do is I will take this equation, wherever n plus 1 is occurring, I am going to replace it with n, right. So, that means, see, I am going to write this as n, right. Instead of n plus 1, I want n here. So, that means wherever n is occurring, you see I shall put n minus 1, replace it with n minus 1. So, then naturally what will happen is that I shall get an equation like minus 2 n minus 1 h n minus 2 c plus 2 c h n minus 1 c. So, this first equation is valid for any n. So, therefore, even if I replace the n with n minus 1, the equation has to be valid, and I did that and I get this as the answer, correct. And now, if you look at this equation, you will find that there is h n minus 2 sitting there, and you have h n minus 2 related to the second derivative of h n. Look at this, h n minus 2 is related to the second derivative of h n. So, therefore, the h n minus 2 occurring there can be replaced with that, right. You can replace it with that, and you have h n minus 1 sitting there, but h n minus 1 is related to the first derivative. So, you can use this relationship, get rid of h n minus 1. So, if you do that, what is the answer? H n minus 2, I am going to get rid of it using this equation. So, I have to replace h n minus 2 with the second derivative of h n, but divided by 2 n into 2 into n minus 1. So, d square h by d c square divided by 2 n into 2 into n minus 1 plus 2 c h n minus 1. I am going to use this equation to get rid of h n minus 1. So, naturally I shall get d h n by d c. I am using this equation. See, I will h n minus 1 is here, but I use this equation and replace the h n minus 1 occurring there. So, the answer is actually just this divided by 2 n. Is that fine? So, if I have done that, well, again I have run out of space. I do not think I shall need this equation anymore. So, maybe, but I will keep it somewhere in case I needed it later. So, where will I write it? Okay, this relationship is there. I will write this equation on top of that. So, having done that, I can remove this equation and try to simplify the equation which I have just now obtained. This is the equation. You can simplify it very easily, but before you do any simplification, let me remove this 2 into n minus 1 there and that, and let me multiply now throughout by 2 n. So, if you multiply it throughout by 2 n, you are going to get 2 n h and c in the left hand side, and that is equal to minus d square h by d c square plus 2 c d h n by d c. This is the result, and just take these two terms to the left hand side. You are going to get d square h n by d c square right, and that is the answer that I wanted. So, therefore, you see that the generating function is actually very useful. I can derive differential equations, and in fact the differential equation that we have obtained is just the differential equation that we had obtained by doing all the manipulations earlier, and therefore this h is actually nothing but the Hermite polynomial Hn. As I told you, these things were already known to mathematicians, and therefore people who are doing quantum physics just had to borrow their knowledge, that is all. But then you may say, well, what is the fun? After all, you could have solved the equation directly, why should you take this? The answer is that once you have this expression, you can derive a very simple formula for the Hermite polynomial itself, which I will do now. Okay, starting from here I can derive a simple formula for the Hermite polynomial. If you want to calculate any Hermite polynomial, I can give you a formula. That is the first thing. The other thing is that in quantum mechanics you always have integrals to be evaluated, and the evaluation of any integral involving the Hermite polynomial is easy to perform using this generating function. Okay, that also I shall demonstrate just for this case, but in the other cases also, that the other cases that we will discuss later, like Legendre or Lagore polynomials, the same procedure is valid, but I will not go into the details. So, what is the formula that I would have for evaluating the Hermite polynomial? Well, suppose I take this function and differentiate it partially with respect to s. After which I will put s equal to 0. What will be the answer? I suggest that you try this. If you differentiate s partially, use this right hand side, use this expression. Imagine that I differentiate s partially with respect to x. After doing the differentiation, I will put s is equal to 0. You can imagine what is going to happen. You will find that the answer must be equal to h1, because you look at the series. Maybe this will become clearer if I wrote the series 1 plus s by 1 factorial into h1 plus s square by 2 factorial into h2 plus etc. That is the form of the series, of this series. So, if you are differentiating with respect to s, right, this 1 will go, this term will survive, it will survive as h1, and then you will have a term involving s, and then higher order terms involving s square, s etc. But the moment you put s is equal to 0, this is going to disappear, and therefore you will be left with only h1. So, therefore, if you differentiate once with respect to s and put the derivative equal to 0, you are going to get h1 of c. If you differentiate it 2 times with respect to s and put the derivative equal to 0, what will you get? You are going to get h2. Differentiate n times and put the derivative, differentiate n times and put s is equal to 0, what will happen? You will get hn, right. So, that is a nice thing. You just have to take this function, differentiate it n times with respect to s, correct, put s equal to 0, you are going to get hn. But that is not the nicest thing actually. The nicest thing is a formula that I am going to show now. So, I can say that HNC is equal to dou to the power of n s by dou s to the power of n with s equal to 0. And that is equal to, well, I do not need these things anymore. that is your S, capital S, correct. This object that I have written is my capital S. So, you will have to do the differentiation, and after doing the differentiation you have to put S equal to 0. Well, the way it is, you see, it looks very tedious to perform this differentiation, because the expression appears very messy, but that is a nice trick which will enable me to evaluate this derivative. This object, I am going to write this as is that okay? Because you see, if you had expanded this, you are going to just get back that, right. So, that is obvious. Now, e to the power of plus e square is there, but you see you are differentiating partially with respect to s. So, this e to the power of c square is not going to be affected. So, I can take it out. So, you will get e to the power of c square dou to the power of n by dou s to the power of n e to the power of minus s minus c whole square. Right. Now, you look at this expression, you see you are differentiating with respect to s, but in the function what happens is that the function depends upon s minus c, right. So, if I wanted, I can say instead of differentiating with respect to s, I can differentiate with respect to minus c, because you see it is a function involving s minus c. So, therefore, I can even say that instead of differentiating with respect to s, I can differentiate with respect to c. The only thing is that an additional negative sign has to be put, right. So, therefore, this derivative I can say it is actually dou by dou c to the power of n, right, but with each differentiation in c there is going to be a minus 1 coming out. So, therefore, what will happen is that I will say okay, it is minus 1 to the power of n e to the power of c square e to the power of minus s minus c the whole square, and of course, I shall have to put s equal to 0. Is that okay? The argument is, you see, going from here to there, you are actually differentiating with respect to s, but in the function the combination s minus c is occurring. That is all that is occurring, and therefore, it is not necessary to differentiate with respect to s, but I can differentiate with respect to c, but c is occurring with the opposite sign. So, therefore, if I am deciding to differentiate with respect to c, I shall put that sign also, right. If you want, you can verify this very easily. You see, you look at the e to the power of minus s minus c the whole square, differentiate it once with respect to s. What will be the answer? The answer is going to be minus s minus c e to the power of minus s minus c the whole square. This is the answer if you differentiate it with respect to s. If you differentiate it with respect to c, what will be the answer? The answer will be minus s minus c into e to the power of minus s minus c the whole square, but you are differentiating with respect to c, that means you will have to put an additional minus 1, right. So, therefore, instead of carrying out differentiation with respect to s, you can carry out the differentiation with respect to c as far as this function is concerned. The only thing is that you have to account for that minus 1. Each differentiation is going to give you such a minus 1, and therefore, I take this and say that okay, here I can differentiate with respect to c provided I put a minus 1 to the power of n. But then again you see that this is very nice, because what is the expression that we have arrived at? The expression that we have arrived at is e to the power of c square minus 1 to the power of n dou to the power of n by dou c to the power of n e to the power of minus s minus c the whole square s equal to 0. But you see now there is no differentiation with respect to s. So straight away I can put s is equal to 0 in here, right. I mean if you had differentiation then you have to be careful, but there is no differentiation with respect to s anymore. So I will just put s is equal to 0, and then what will happen, I will get a formula which is quite nice. What does it say? It says e to the power of c square minus 1 to the power of n dou to the power of n dou c to the power of n e to the power of minus c square. And even partial derivative notation is not necessary now, because the derivatives are operating only upon a function of c. So therefore if you like you can say, okay, this is d to the power of n dx to the power of n. So what is the result that I have obtained? It is a nice formula. HNC is given by e to the power of c square minus 1 to the power of n d to the power of n by dx to the power of n e to the power of minus c square. This is the formula that I can use. If you want any Hermite polynomial, I can evaluate it using this formula. And just to illustrate, suppose you think of H0 . This will be H0, which actually is really unnecessary for me to write it down because it is so simple. T to the power of 0 means you are not carrying out any differentiation, and minus 1 to the power of 0 is 1, and so e to the power of c square e to the power of minus c square, the two will cancel, you will get the answer as 1. Simple and straightforward. Let me just very quickly evaluate H1. Right, you just differentiate this once, e to the power of minus c square 1 minus 2c will come down, and this and that are going to cancel, you will be left with just 2c. So this is your H1. Okay. Now it is it's a very easy. All that you have to do is you have to go on differentiating. If you wanted H10, the only thing is you have to differentiate 10 times, which you may say, well, it is not very easy to differentiate 10 times. But there are, as I said the other day, there are programs like Mathematica. Mathematica can evaluate even the 100th derivative. The expressions will be messy, but it can do it. Okay. Now you can evaluate H2. Well, I think it turns out to be, well I will check this because I do not want to make a mistake. You can easily evaluate it, but maybe I will just copy it from the book. That is H2, similarly H3, goes on. So, now let us summarize what we have found. What we have found is that the solutions are acceptable only if E is given by n plus half h nu. And then what is the solution? The solution is actually psi equal to e to the power of minus c square by 2 multiplied by h. This h is in general a polynomial. If you are thinking of a particular value of n, the polynomial actually will be the Hermite polynomial Hn of c, which has a degree equal to n. The degree of the polynomial, that is the highest power of c, will be n, and it will be this. Hn, you can evaluate it using the formula which was originally derived by Hermite, I believe. Formula is e to the power of c square minus 1 to the power of n d by dx to the power of n e to the power of minus c square. This is Hn. But then once you have the wave function, what do? You try to get physical information out of it. The function, you have to ensure that it is normalized, and the way this psi is written, it is not normalized. So, there will be a normalization factor. I will introduce it now. I will call, I mean, this is just the normalization factor. You give me any wave function, I will normalize it, and the normalization factor will in general depend upon the number n. This number is a quantum number. See that you should also remember that this is a quantum number that has arisen. How did it arise? I imposed the acceptability conditions, and then in the process of solution this number came out naturally, right. It was there in the solution. When I imposed the acceptability, the condition that the wave function is acceptable, I automatically got this number. The solution was dependent upon that number, and this number can take on the values. In the case of the harmonic oscillator, it can take on the values 0, 1, 2, 3, etc. Right. I think this is a right point for me to stop. I shall continue in the afternoon. Thank you for listening.